So today we will discuss the differential equation of order n. Say differential equation of this form. This form is called exact when it can be derived by differentiation only and without any further process from an equation of the next lower order of this form. That means the differential equation of n order is said to be exact when it is obtained from just immediate next lower order by differentiating once. That means this equation is obtained from this equation by differentiating this equation once. You see, this is of n order, this is of n minus 1 order, just immediate lower order. So you can see in example. So this is an exact differential equation because this differential equation can be obtained by differentiating once this equation. So what is the order of this differential equation? The order is 1. Now what is the order of this differential equation? Order is 0. So 0 is just 1 less than 1. Okay. So this equation has been obtained by differentiating this equation. So you can check, just differentiate it, you will get this equation. Therefore, this equation is an exact differential equation. Now we will see that there is a condition required for a given differential equation to be exact. So let us discuss here. So condition for exactness of a linear differential equation of order n. Let a given differential equation, let this equation be exact. That means that this is our hypothesis that this equation is exact. Now we are going to find the condition for this equation to be exact. What is the condition required for the equation number 1 to be exact? This is an order differential equation where p1 was p0, p1, pn and phi x are all functions of x alone. These coefficients are all functions of x alone. And our hypothesis is that this equation, that is equation 1, is exact. Our objective is to find the condition for the exactness of equation number 1. Okay. So up to here we have assumed that equation 1 is exact. Now by definition of exact differential equation of n order, if the equation 1 is exact, then it can be obtained from the equation of next lower order simply by differentiation. Okay, this is by differentiation of exact differential equation of n order. So we assume that equation 1 can be obtained by differentiating this equation. So in view of the definition of exact differential equation of n order, we assume that equation 1 is obtained from this differential equation. We have the equation 1 which is of n order. This is of n order. If this is a exact differential equation, then it must be obtained from a differential equation of n minus 1 order. So this is n minus 1 order. That means on differentiating this equation 2, we must get equation 1. So on differentiation, this constant term will become 0 and this integration symbol will also be removed. And finally we will get equation 1. So up to here it is our hypothesis. Now let us differentiate this equation. Now we are going to differentiate this equation 2. How to differentiate this equation 2? So we have product terms. So this is a product of p naught and this derivative. This is a product of q1 and this derivative and so on. This is a product of qn minus 1 and y. We know that p1, p0, q1 ... these are all coefficients. These coefficients are of function x alone. So to differentiate such terms, to differentiate this product term, we have to use chain rule. So you know chain rule. In chain rule, what we do? So we will consider once this as a constant, p naught as a constant, and differentiate this equation with respect to x. So what is the differentiation of this term with respect to x? Differentiating once, this term will give you dny dxn plus this time you consider this term as a constant and differentiate p naught with respect to x. Differentiate p naught with respect to x. So it will give you p naught prime. Okay, p naught prime. So it is on in rough page here. P naught prime. Differentiation of p naught with respect to x is denoted by p naught prime. Similarly, you use the chain rule to differentiate this term, and all these terms. And finally, make a rearrangement by looking for the coefficients of dny dxn, dn minus y dxn minus 1 dot 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 dy by dx and y. Finally, you will get this equation, equation 3. This is plus dot 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 equals to 5x, which is equation 3. Okay, just ignore this not part, just ignore it. So this is equation number 3. So what is equation 3? Equation 3 is obtained by equation 2 from 2 by differentiation. Now equation 1 and equation 3 must be the same equation. Why it is so? Why equation 1 and equation 3 must be same? Because it is our hypothesis or assumption that equation 1 is obtained. It is our assumption that this equation 1 is obtained from equation 2, from this equation, just by differentiation. It is our hypothesis. And what is equation 3? This equation 3 is obtained from equation 2, this equation 2, by actual differentiation. So equation 1 and equation 3 must be same. If equation 1 and equation 3 are same, then the corresponding coefficient terms will be same. So by comparing the corresponding coefficients of these terms in equation 1 and 3, we get this coefficient. This coefficient is from equation 1, this coefficient is from equation 2. So P1 is the coefficient of what? P1 is the coefficient of, in equation 1, P1 is the coefficient of dn minus 1. So this is actually dn minus 1 y dx n minus 1. So this coefficient must be equal to this coefficient, and this coefficient must be equal to P2 of equation 1, and so on. Finally, this coefficient must be equals to the coefficient of y in equation 3 must be equal to coefficient of y in equation 1, it is Pn. So we get the relation like this. Okay, so P1 equal to this one. Just by rearrangement, Q1 equals to P1 minus P0 prime. This is equation number 4. Similarly, Q2 equals to from this equation, you see, from this equation, Q2 equals to P2 minus Q1 prime. Q2 equals to P2, this P2 minus, it should be Q1 prime. So instead of this term, it should be Q1 prime, but Q1 prime is equal to Q1 prime. We can obtain Q1 prime from this equation just by differentiating this equation once. So on differentiation, this will become Q1 prime P1 prime minus P0 double prime. So there is minus common. So finally, Q2 equal to this one, which is equation number 5. So similarly, comparing other terms, comparing the last second term, comparing the coefficient of the last second term in equation 1 and 3, we get this relation. And also comparing the last term in equation 1 and 3. Last term means we have to compare the coefficient of y from equation 1 and equation 3. We get this relation. So this is the coefficient from equation 1 and this is coefficient from equation 2. So again, by differentiating equation 6 from equation 6, differentiating this equation with respect to x, again we get this relation. So what is the differentiation of this? It will give you this one. So this is the differentiation of this term, this is the differentiation of this term, and so on. This is the differentiation of this term. But what is Pn? Pn is nothing but Qn minus 1 prime. So differentiation of this term will be Qn minus 1 prime. Qn minus 1 prime is nothing but Pn. So this is the relation. Actually. This is the final relation. So taking all the terms to one side, that is left hand side, from this equation we get this final relation. This is the required relation. So equation number 7 is the required relation for the equation number 1. The given differential equation of n order to be exact. So this is the final required relation. Again, by putting the values of q1, q2, q3, qn in equation 2. So we have all the values of q1, q2, qn. This we have already obtained. So putting the values of q1, q2, qn in equation 2. What is equation 2? This is equation 2. So we have to put the values of q1, q2, qn in this equation. Finally, we get the relation, final equation, this equation. So what is this equation? So this equation is nothing but it is the solution of the equation 1. This equation 8 is the solution of equation 1, given differential equation. So which is given, which is written here. Equation 7 is the required condition for the exactness of equation 1 when the condition is satisfied. So when the condition is satisfied, or when the differential equation 1 is exact, the solution of the equation 1 is given by equation number 8. Okay, so this is the required condition for the exactness of equation 1, and this is the required solution of the differential equation 1. So in the next video we will discuss some problems related to this.